Okay, welcome back everybody. We are on chapter 7, which I am calling the closed form solutions to linear ODEs in one dimension. And really what we're on is the chapter that I'm kind of required to put in this course because everything we're going to cover in this chapter is basically what people are going to expect out of you once you tell them you've taken an ODE course. You're going to be like, oh, you can solve constant coefficients equations, you can solve Cauchy-Euler equations, you know about fundamental set of solutions and the associated homogeneous solution or homogeneous equation to an inhomogeneous problem, and so on. So that's what we're doing in this chapter. And something else that's kind of nice is in some senses, chapter 6 was like the sledgehammer, and it was a really hard chapter. So it's a little hard to understand the chapter. It's a little hard to work through problems in the chapter. And all of a sudden, moving to chapter 7, we start moving slower in the class because there's kind of more tiny things to cover, and the problems actually get easier because they're a little bit more straightforward. And that's why it makes sense that this is kind of the stuff covered in your generic ODEs course, because it is the most accessible probably out of everything we're going to cover this semester. So your generic ODE student will cover this in a semester and a few things in our nonlinear section, and that would be about it. And everything else that you've covered is kind of extra that you can impress them with. Okay, so section 7.1, we're just going to talk about, this is kind of another glossary section, so we're going to give some definitions, and we really want to pay attention to these definitions because this is, if we're in a future course that's relying on ODEs as a prerequisite, these are the definitions that they might throw at you and expect you to remember. So if we start at the nth order linear ODE in one dimension, being in one dimension really makes my life easy, and I can represent any nth order linear ODE as, you know, this is the sum of j going from 0 to n derivatives. So we're looking at the number of derivatives on my unknown y, and each one of those y's can possibly be multiplied by a function. But thankfully, this is just a one-dimensional function. So what are the linear, really the linear multiplication operators in one dimension? We don't have matrices anymore. We just have scalar multiplication. So this is scalar multiplication of functions m, and they each multiply the derivatives on y, and it's possibly equal to another function at the end. And so what's like a classic example? If I expanded this out, let n equal 3 or something, this would be like t squared y with 3 primes on it plus cosine t y with 2 primes on it plus e to the t y with 1 prime on it minus 3y equals, we'll make f tangent or something. Okay, so that's like your, you know, an example of this. If I expanded the left-hand side as, you know, its actual sum, you have the sum of the 0th derivative, some function, the first derivative, some function, the second derivative, another function, and the third derivative and some function. And you can go as high as you want, and you're just allowed to multiply by functions, but do nothing else. And that's going to be your classic linear ODE in one dimension. There's not really any sort of other linear ODE in one dimension. And then this is jumping back to our previous chapter, right? We're going to call the equation homogeneous if our forcing function, which is whatever sits on the right-hand side, is equal to 0, and we're going to call it inhomogeneous if it's non-zero. So if I get lucky and the right-hand side just has a 0, it makes my life a little easier. We call that homogeneous, and if it's non-zero, we call it inhomogeneous. So here's an example, I guess. This is an example of a homogeneous ODE because notably the right-hand side is 0 here. You know, potentially you could put like an additive function on the left-hand side. You'd have to bring it over to the right-hand side, right? We need to like try to rewrite it in this form, which in the current state it is in that form, and then we check the right-hand side and we check if that's 0. Meanwhile, if I modify the right-hand side and I instead recover something like t squared plus 2t plus 1 on the right-hand side, we're inhomogeneous because the right-hand side is no longer 0. To describe the summation notation, I've kind of described explicitly what each of the mj's are going to be. So mj is m2, the top order, is t squared. That's because it's the m that multiplies the top order, and then I have 2 derivatives on y. m1 is 2t, that's multiplying the first derivative. m0 is just 1, that's multiplying the 0th derivative. And then f of t is the right-hand side. Okay, so this is kind of the first thing we really need to focus on is this next definition, which I'm calling the fundamental set of solutions. And we're going to notice here that my ODE is homogeneous. Okay, if I talk about a fundamental set of solutions, we're talking about a homogeneous ODE. So just keep that in mind. Fundamental set is necessarily associated to a homogeneous ODE. But given one of those, given a homogeneous ODE, and especially in this case we're just going to make it nth order, given a homogeneous ODE, as long as I can find n linearly independent solutions, That's the important thing here. I'm looking for a set of n linearly independent solutions. Because when I call it a fundamental set, it's a set of solutions, and they all must be linearly independent. And so each of these solutions, the y, well, I'm calling here y sub k, each of these y sub k's for k varying between 1 and n, each of them solves my homogeneous differential equation, and they must be linearly independent. Okay, so we have this nice lemma, which says that an nth order linear homogeneous ODE in one dimension always has a fundamental set. So we can always find one of these. Really what the lemma comes down to is the fact that we're taking n total derivatives on y. Every time I take a derivative, I lose a constant, right? When I take one derivative of a function, a constant disappears. If I take a second derivative, two constants have disappeared, and so on, right? I guess, technically it's polynomials up to degree n minus 1 have disappeared at the point that I get to n derivatives. And what is the dimension of polynomials of degree n minus 1? Well, they're exactly of dimension n. And so that's why I can always find this linearly independent set. It's because that the null space of the operator, which is right here, is necessarily of dimension n. And null space, of course, corresponding to the operator on a function being equal to 0. But the way I prove it here actually is a little bit more involved, but also maybe a little bit more, it relates to chapter 6 a little bit. I can rewrite an nth order ODE in one dimension as a first order ODE in n dimensions. I know I'm really drilling that into you. That's one of the theorem. Yeah, theorem 4.4.1 lets me do that. And if I do that, I convert this ODE into the first order ODE in n dimensions, and I just recover that y as a vector in n dimensions prime equals some matrix on y. And we necessarily know that there exists a fundamental matrix, right? That's what theorem 6.55 told us. And it turns out then that the n vectors comprising the n columns of the fundamental matrix necessarily form a linearly independent set of solutions. So we basically gain, I shouldn't really say that the n vectors, it's the n vectors. If you look at the first entry, so the first entry of the n vectors forms the linearly independent set. So that's how you can find it in an alternative manner. So there's lots of reasons that we can guarantee this exists. Okay, so we jump back. This is the same ODE that we were studying earlier up above. Make sure it's homogeneous if we're looking for a fundamental set. This is the same one we were looking at above. And I'm going to claim that these two linearly independent solutions form a fundamental set. All I need to do is show that they actually satisfy the ODE, and second, that they're actually linearly independent. To do that, you should all know how to show that these satisfy the ODE by now. You're just going to take this function and plug it in for each term and cross your fingers that it actually equals 0, right? This is a solution to the equation. And then the fact that they're linearly independent is pretty easy to see because there's at least one spot where the function of cosine is not a multiple of the function of sine. And that would be any time that like sine is equal to 0, no multiple of sine is going to give you cosine at that point. And so that's how you know that they're linearly independent. So therefore we have this set, which is a fundamental set of solutions, and we just group them together into a set, right? If we've found two linearly independent solutions, we just group them together and call that the fundamental set. So now I'm going to, this is related to homogeneous ODEs. And now we're going to shift over to inhomogeneous ODEs. What does it mean to solve one of those? Well, if we're given just a generic inhomogeneous linear ODE here, then we grab a fundamental set of solutions to the associated homogeneous ODE. So what I've done is I've taken f and I've converted it to 0 to recover an associated homogeneous ODE. So all we do is we start with an inhomogeneous one, and we reduce the right-hand side to 0, and then we extract a fundamental set of solutions for that particular homogeneous ODE. We then say that the function YH, which consists of all linear combinations of the fundamental set, we call that the general homogeneous solution. So even though this is really the ODE I'm looking at, I call this solution, which solves the homogeneous one, the homogeneous solution. And I give it a little h on the bottom to let me know, hey, I'm talking about homogeneous solutions. And I can just form, this is a linear combination, right? These C's are just some constants, and then I have the YJs from my fundamental set. This is exactly how we constructed linear combinations of sets in linear algebra, or in other senses, this is the span, right? This is the span of y1, y2, ... yn. It's the span of my fundamental set. That's called the general homogeneous solution. I then look for a particular solution. So a particular solution, which is what I'm going to call y sub p, p for particular, is that word, any solution to the, I guess I called it non-homogeneous there, I should probably call it inhomogeneous, even though you can use either language. The inhomogeneous ODE, if I can find any solution, I just need to find a single solution to this, and I'm going to call that a particular solution. It turns out we only care about finding one particular solution. Even though there are many, we only care about finding one. And I'll show you why in a bit. So we call that a particular solution if it actually solves the inhomogeneous ODE. If I move down just a little bit, I then call the general solution to the original ODE. This is the ODE with an F on the right hand side. The general solution to the original ODE, which is inhomogeneous, is, and I drop the subscripts H or P, it's the sum of the general homogeneous solution with any particular solution. And so what we see here is there's our span of the fundamental set, and there's our particular solution. So the general solution to any ODE is the sum of the general homogeneous solution, aka the span of fundamental set of solutions. It's the span of the fundamental set plus any particular solution. And it's plus any particular solution because the particular solutions only differ if for some reason I've found two particular solutions. It turns out they can only possibly differ by elements of the homogeneous solution. So this kind of considers all of the particular solutions at once. The way I want to think about this is that this is kind of like the antiderivative, and this is like plus c. Right? We know that we can find an antiderivative of a function, but we find every antiderivative of a function if we add plus c onto the end of it. So that's really what's going on with these ODEs, is our plus c is more complicated because it's a differential equation. We're taking n derivatives, and so it's more complicated than just plus c. But the idea is that we have found n antiderivative, and then we're able to add constants. These are really the constants, and then the homogeneous solutions is akin to adding plus c for finding antiderivatives. And so just the same way that in calculus your professor would be very angry at you if you forgot a plus c when you were giving solutions, I'm not going to be very happy with you if you forget to add your homogeneous solution onto your general solutions to ODEs. Sometimes I may only ask you to find a particular solution, and that's fine, but if I'm asking you to find a general solution, I better see the addition of the homogeneous solution, just like we should see plus c's with antiderivatives. Okay, so let's actually go through this full process then. If we're given an inhomogeneous ODE, this is the one we approached at the start of the section, an inhomogeneous ODE, and for some reason I already know my fundamental set, right? We looked at the fundamental set earlier. So given this associated homogeneous ODE, which recall exists when I drop the right-hand side. So I take the right-hand side and I let it go to 0. That's how I get an associated homogeneous ODE. Then I'm able to find a fundamental set of solutions for that. We don't know how to necessarily yet, but if for some reason I'm given a fundamental set of solutions and I'm given a particular solution, then I can form the general homogeneous solution is just the sum. It's the span of the fundamental set, YH. I have a particular solution right there. For some reason, we just assume I know it. And we'll talk about how to find these later. So I found a particular solution, and then my true general solution to the entire differential equation is the previous two added together. So I'm going to take YH, which is right here, and I'm going to take YP, which is right there. So YP is over here, and I'm going to add them together, and that's going to give me my general solution. And it's called general because you can check that for any choice of C1 and C2, the ODE will be satisfied. So no matter what C1 or C2 I grab from this and I plug it into my original ODE, which is up here, the original inhomogeneous ODE right there, any of the choices I make for C1 and C2 will solve this equation. That's why we call it general. Okay, then I make a very brief remark on, saying that maybe the reader is a little interested as to where I came up with the fundamental set and where I came up with my particular solution from. That's the rest of the chapter. So we'll get there. This is really a glossary. I want us to get used to two things. The first one is just the names, homogeneous, inhomogeneous, associated homogeneous, right? General solution, so general homogeneous solution, particular solution, and general solution. Oh, and I suppose fundamental set. Which I'll call FSS. So fundamental set of solutions. So these are the words that really I want us to focus on memorizing for today. And then basically the rest of the chapter is going to be like, okay, how do we actually go through this process? All right, that's all I have. Thanks for sticking with me. See you in class.